So at this point in time, it's my pleasure to introduce you to Dr. Sarah Cox.
Thank you so much, Erica. Hi, everyone. My name is Sarah Cox. I am an assistant professor at Michigan State University. I teach primarily the math methods class for our students in special education, and I also teach a class in autism spectrum disorders. So, a little bit about my background. I was a general education math teacher for about 3 years in the state of South Carolina. I was teaching middle school, and then I found a deep passion and interest in supporting students with disabilities who were in my general education classroom. And so I decided to go back and get my doctorate in supporting those students. The students with autism spectrum disorder are kind of my focus. And so a lot of the research that I do is on supporting language and the language of mathematics. So that is just a little bit about my background. And today, this talk is going to be about graphic organizers and primarily graphic organizers as we're thinking about kind of the language of mathematics and using these graphic organizers to support our students in that way. So, when I talk about the language of mathematics, there's really two different features or components of that language that we're talking about. There's the receptive piece of it and the expressive piece of it. So, receptive language is all of the information that is coming at our students and how they are kind of trying to understand the environment around them. And in the case of math, this, of course, is not only that spoken language that we are giving to them and how we are trying to communicate it, but it's also what we're writing on the smartboard, what they're trying to read on the worksheet or in the textbook. It is what their peers are saying to them. All of that information that they are trying to gather and process in their mind is all part of receptive language. And then, of course, expressive language is the articulation piece, how they are communicating their own reasoning or their own thought process. And this is not only articulation expressively so that other people can understand them, but also that piece of how they are trying to formulate those thoughts and put them into some kind of way to communicate it, whether it's words or diagrams or some other type of expression. So, what this specifically looks like in a classroom is as students are trying to make connections between concepts. So, for those of you who are familiar with the process standards of mathematics or the strands of mathematical proficiency, we talk a lot about how important it is for students to make connections between these concepts so that they are able to build those really strong connections and draw from prior math knowledge to support that the new thing that they are learning. And in order to do that, in order to not think of these as distinct, separate things that we are teaching them, but to draw those connections, they have to use that receptive language in order to do that. They also have to be able to reason abstractly. And this is, of course, is particularly important as we go along in the grade levels. So math tends to be relatively concrete in those early ages. And then as we move into third, fourth, fifth grade and beyond, the math concepts that we are teaching become much more abstract and they have to be able to reason through that. And then the other piece of receptive language is that they are creating mental models. So, what does something look like? Or what are they connecting it to from their prior knowledge in order to help them make that transition from short term memory into long term memory? For expressive language, this looks like they are able to communicate what is happening, why it is happening, and how that thing works. So it's not just that they are able to follow the procedures that you have taught them that day, but they are also able to communicate what those steps are, why those steps work, and how, mathematically speaking, how that is possible. So that, again, we're helping them from a cognitive science standpoint, we're helping them transition from they are there in that moment being supported by you in your classroom, and they are then also able to do that thing independently and move it from that short-term memory to long-term memory. And that they're able to recall it again at a later date and reason through whether that thing makes sense or not. Expressive also relies on this precision of terms. So Sarah Powell and her colleagues have done work on terminology in mathematics, and they found over 500 new vocabulary words introduced just in fifth grade mathematics alone. So the number of terms that students are being asked to learn really does make the language of mathematics a second language, third language, fourth language for some of our students that they are having to learn. And so learning to be really precise with these terms and what they mean can help aid their understanding of these nuanced concepts that we are trying to teach them. And then last but not least, again, going back to our process standards of math, what we are asking students to be able to do, we are asking them to be able to justify choices that they have made and also critique other people's thought processes. So there is not always a right way and a wrong way to do things in math. There are oftentimes multiple ways to get to an answer. And students need to be able to justify why they have done it, how they have done it, that it makes sense, that mathematically their answer is reasonable. And they need to be able to look at someone else's work and understand whether that is or is not mathematically appropriate. And in order to do that, they need these expressive language skills. So, to help them with all of these important aspects of engaging in mathematical learning, we can use graphic organizers. So, there are several studies that use graphic organizers in different ways, and they promote different aspects of mathematical learning. All of these links are available at the end of the PowerPoint, and they're all hyperlinked in the PowerPoint as well if you are interested in reading the research specifically. There have been several studies who have looked specifically at graphic organizers and their ability to improve conceptual understanding. So, when we talk about conceptual understanding, Bethany Riddle Johnson has done a lot of work in looking at what is the link between students' conceptual understanding, so their idea of the mathematical concepts, why things work the way they do, procedural understanding, which is the step by step, what are we doing in math in order to get to our answer. And the third kind of component that her team has found is procedural fluency. So students' flexible thinking around the procedures, how they work, what's the most efficient procedure to use, what's an effective procedure to use. And her team has found that this is a really iterative process for students, that it's not linear. There was a time that we thought you had to teach concepts first and then procedures, but what we are finding is that we're teaching all of these things simultaneously, and that the better students are able to understand the concept of math, it will help them with their procedures, which helps them become more procedurally flexible. And again, this is just really iterative, and students are learning all of these things at the same time. So, with that being said, when I say conceptual understanding, that is what I am talking about, is that construct. And Fabros and Ibanez and Avez have done these two studies and have found that graphic organizers can, in fact, support students in their conceptual understanding and improving that conceptual understanding. And we'll see some graphic organizers here in a minute that are built to do just that. The other thing that they can do is enhance planning and monitoring. So, for my fellow middle school aged people, you know that this planning and monitoring, which many of us refer to as executive functioning skills, a lot of executive functioning skills are the ability to plan and then self monitor their own progress within that plan, all fall in this. This is a study that I did with a colleague, Brie Jimenez, and we looked at different math um, excuse me, different strategies in math. And one of the things that we found was, especially for our students with disabilities, supporting this planning and monitoring process is really important. And there are several other studies that talk about executive functioning and how we can support that, particularly in the area of mathematics. The third kind of area that graphic organizers can help with is the vocabulary piece specifically. So, as I mentioned, several new hundreds of words, in fact, are being introduced in mathematics. And so we can use graphic organizers to support this additional vocabulary for students. And here are two studies that specifically have done that. And then last but not least, we can also use graphic organizers to help our students improve in their written and spoken communication. And here are two additional studies that have found positive effects for improving this part of math communication and math writing. All right, so I'm going to show some examples of math organizers, graphic organizers here in a couple of minutes. And then we are all going to practice using graphic organizers for math in some different ways. But when we are talking about types of graphic organizers, generally speaking, there are three different types of graphic organizers that we can use. The first one is a sequence chart. And in a sequence chart, there is a very specific order. So things need to be presented in a specific order. And we can use visual cues in these sequence charts to help specify that this is the order that students need to follow. So in this particular sequence chart that I have created, you can see that there are numbers and arrows that demonstrate that this is the order that this thing needs to happen in. We present events or procedures in orders. We need to make sure that we're making the order clear using those visuals. The recommendation is to use numbers to help students recognize that this is the specific order that they need to go in this sequence chart. The second type of graphic organizer is a hierarchical diagram of some sort. So in this hierarchy, we have the primary topic, and then there are main branches, and there can be sub branches off of that main branch as well. We typically link these branches with some kind of visual aid again. It can be arrows, there can be lines. We can color code these main branches. You can see here that I've made the main topic, the hierarchical diagramming, solid yellow, and then the branches that come off of it are dedicated as or indicated as sub branches because they are white boxes with the yellow outline. But there are different visual cues that we can give to students to demonstrate that these are sub branches that are coming off of this main topic area. And then last but not least, the third type of visual or graphic organizer that we can use is a compare and contrast chart of some sort. The most common type of compare and contrast chart, of course, is a Venn diagram. And in a traditional Venn diagram, we have two overlapping circles where we are showing that there are differences on the external circles, and then those similarities are the things that are overlapping there in the middle. Graphic or Venn diagrams can also have more than one, they can have, or more than two, they can have three different overlapping charts, and then there are different versions of this that we can use that are just trying to really highlight for students what things are different between these constructs and what things are overlapping, what do they share in common. So I'm going to go through 5 different types of graphic organizers and how they have been used in mathematics here with you. You'll see examples of these 3 types of graphic organizers within those examples, but this is kind of the overview of what types of graphic organizers exist, what are the kind of categories that they fall into, and then you can be thinking about for your own math instruction what kind of topics might fall best within these three different areas. All right, so the first example is a Freyer model. Freyer models traditionally for mathematics have been used to support vocabulary development primarily. And the idea behind a Freyer model is that you have a term, that term goes in the middle of our box, and then there are four additional components that we are teaching students. So the numbers that you see here go along with the order in which we recommend you actually have students complete these Freyer models. So the first thing that they're going to do is they're going to write their term in the middle there. The term that we have here in this example is linear function. That's the very first thing that we're going to do. The second thing we're going to do is actually complete the box that is about the characteristics and the visuals of what that term is. So for linear functions, we can see that I have written here that it will always be a straight line on a graph. I've added additional visual cues for myself to the word always and straight line so that I can help my brain think about what a linear function means. I've also added two visual examples here, both a graph of what a linear function is going to look like, and then also the XY chart of what that pairs with. And then you can see in blue there that it says for every +2 right, there are -2 down. So again, another kind of verbal or written component to add to what this thing really looks like. The third thing that students are then going to do is they're going to provide themselves with examples. So again, if we think of kind of the way that the Freyer model is taught and how it relates to our own mental thought process and our teaching for that matter, we are teaching students when we have a new term, we are teaching them what this looks like in math. And so that's why we do characteristics and visuals first. The next thing that we teach is examples. So what are example linear functions? And you can see here that again, I've shown another visual example of what this looks like. So I've given an XY plot. I've shown different X values and those Y values that are associated with it. You can see that as X increases by 3, Y is going to increase by 7. I've used different color markers to show this on the XY, the function plot. And then you can see the graph that is associated with it there on the right. You can also see in orange here that I have drawn a star and said that the lines can go any direction. And then I've given some different examples of what those linear functions might look like. The way that I often used Freyer models in my classroom for math instruction was as a dictionary of sorts. So as we started a new unit, students would get a packet of Freyer models. And as we went along, the students would fill out new terms as we came to them, and they would create these Freyer models for each of those terms. As such, you can think of each of these like new main color markers as a new day. So when the term linear function was first introduced on that day, the green marker of it's always going to be a straight line was probably the first thing that I taught that day. And then other days when we came back and we kind of refined our understanding of what linear functions were and were not, were often marked either in a different color, or you can just think of these different colors as the students are coming back in and they are refining their own understanding of what this thing is, what this term means, and what it looks like. So examples are the third thing that we teach, and then that orange marker is probably a different day the student's coming back and they are further refining their understanding of what linear functions are. Because in the first iteration of this, students are probably thinking that linear functions are this very traditional upward slope, increasing positive slope. And we want them, of course, to get to the point where they can understand that linear functions can be in other directions. So that's the third thing that we teach. The fourth thing that we teach are non-examples. So what are things that are not linear functions? And we want to choose non-examples really strategically. And of course, these non-examples are going to be both functions that we are teaching them that are not linear functions, but other types of functions. And then also really standard kind of common misconceptions or common errors that students make about what a linear function would be. And of course, the very traditional one is the straight up and down vertical line is not a linear function because there is no change in the y variable. So not only have we given them this idea of a non-example is this vertical line, but we've also provided the rationale for why that thing is not, in fact, a linear function. So that those are now our non-examples, and they are very strategically placed in this graphic organizer as non-examples so that a student can look specifically at this Freyer model and they can look for what are examples, what are non-examples, and they can refer back to this Freyer model to help them in their thinking, and they can continuously add to this Freyer model as they are refining that thinking. And then the last part of this Freyer model that we actually fill out, which is probably different than those of us who used Freyer models in school. So I know when I was a student, I used Freyer models, never in mathematics, but we did use them in language arts. And the very first thing we did was we filled out our definition. We flipped to the back of the book, we filled out our definition. And what we know from again, from a cognitive science standpoint is instead of completing the definition first, which is this really abstract language that we are attaching to this term, we actually do the definition last. So once the student has what are the main characteristics that make this thing true in mathematics, what are some examples and non-examples of this concept or this construct, the very last thing we do then is provide a definition. And the definition, of course, is going to include not only the textbook definition, and so the purple font there is what the textbook would say this thing is. It's a rate of change. The rate of change is constant between two sets of points. The green there is the equation, of course. Y is the function of x when a plus b x, or a plus bx. And then again, you can think of this little star orange as at some point the students are being introduced to additional knowledge, and that additional knowledge is that the b value cannot equal 0. So this is something that we can continuously refine. These are things that, again, I personally, as a teacher, I use them as a dictionary of sorts, and the students could refer back to those things. You could also use these as a continuous like word wall. I've seen teachers put things up on their word walls, and as we are learning as a class together, we can go in and refine these different ideas together. So those are just some of the ways that we can use Freyer models, but traditionally they have been used to support vocabulary in mathematics. I'll give you an example in a little bit of how else they can be used, but that is traditionally how we have used them. All right, a second type of graphic organizer for math is a mind map. So this, again, these mind maps are the hierarchical part of graphic organizers. So we have our main topic, which in this case is division, and then we are kind of branching off into different things. So this is a mind map that was made for division. It was made by one of the students that I was working with. I cleaned it up a little bit. He hand wrote it, but I cleaned it up a little bit. Now, as teachers, we can make choices in terms of how is this thing visually presented, right? I wanted to put this here to show you kind of how his thought process was working. So he was thinking division was the thing, and then it was helping him as he was thinking about, okay, so when she's saying dividend, what she's really talking about is the number that's being divided. Let me write that down so that I know what that is. When she says the word divisor, what she's talking about is the number of groups that it's being divided into. And the quotient is then my result. So he was writing those things down kind of in the moment to help him remember. And then and then of course we got to remainder, what happens when we have a part of the dividend that cannot be divided equally. And so then after that, we added these examples of what does this look like when a division problem is written in this a cross way, 48 divided by 8 equals 6. And then when he was doing it, he was color coding it. So I had different color highlighters and he was circling, and all of the divisor was one color. All of our quotients were a different color. All of our dividends were a different color. And then remainder, of course, was a different color. And then we added this link between the dividend and the remainder, because the remainder, of course, is part of the concept of our dividend, because it's that portion of the dividend that cannot be divided equally. So when we are teaching, we might choose to present something using a mind map. And if we do that, we might decide to present it in a much more linear fashion. We might put division at the top and then break these out into separate ideas and present dividend first, and then divisor, and then quotient, and then our remainder, which is perfectly fine. In this particular case, I was using a mind map to help the student organize his thoughts as we were working together. And so I wanted to represent mind map for you in this way, that it was a very fluid, kind of natural part of instruction. And this is how he was helping himself take that internal thought process and make it more of that external idea of what does this visual model look like in his head, and how are we connecting these different concepts to help him remember what these things were. And then, of course, this became a tool that he could refer back to, both as we were working together and as a tool for himself. So when he would go into class and his teacher was saying something about the divisor, if he needed that visual cue of what is my divisor, he could go back to this visual mind map to remind himself of which one of these numbers is going to be that thing. There are, in the links that I've given you, there are 3 different online platforms that I have used that students enjoy. They have very different structures. They have different pros and cons. So I would encourage you to look through and see which one works best for you and the students that you work with. But they are Canva, and Canva, of course, offers free educational memberships for any teacher. You just have to sign up using your .edu account. Canva has great tools. This example right here, this idea mind map, one of the things that I absolutely love about Canva is they have templates that are already available on there. And in those templates, they walk through and help you set up how this works. And they give you little tips about, so up at the top, you can see, to focus better, consider setting a time limit for creating your mind map. the flow. You can generate more shapes by clicking on the arrows in their side. So not only are they helping you set it up, but they're also giving you kind of tips and tricks about managing your own, mental states and the physical interaction with the tool itself. So this is just one example of what is available on Canva. The other two that are available in the links are Coggle and MindMup. One of the great things about MindMup that I really enjoy is that there is a live interactive function. And so when I am working with small groups of students, I will often use MindMup because we can all be in the same mind map at the same time and we can be talking through the creation of that mind map together. And if we have time during our presentation today, that is something that, of course, we can look at together, explore together. All right, so our third example is the Venn diagram. And as I mentioned, the Venn diagram is the most commonly used type of compare and contrast graphic organizer in math. In this particular example of a Venn diagram, we are looking at the mathematical idea of let's find our multiples of 3 and our multiples of 5. And then I've used the two different colors again to provide just an additional visual aid of what are multiples of 3. They are all listed here in orange. What are multiples of 5? They are all listed here in blue. And then the dark gray, the slate gray in the middle there are multiples that are shared by both 3 and 5. Again, from an instructional standpoint, there are a lot of decisions that you can make here as an instructor. So the way that this is kind of presented is we as a class are working together and we are thinking through multiples of 3. You can see that I have listed them here in hierarchy. So 3, 6, 9, 12. When we get to 15, we're going to have the conversation about where does 15 go? Is it only a multiple of 3? Is it also a multiple of 5? That's how we know that it's going to go here in this overlapping area. If this is something that students are doing in a group independently, some of them may choose to just start listing multiples of 3 and 5 that they know themselves. If they end up listing them in like the straight traditional line way, so I know when we're finding greatest common denominator, we often show students write 3, write 5, put your colon, and then just list all the multiples that you know. And so you'll have students that will do that, and then they will circle those common multiples. And then again, if we put them in this Venn diagram, it will look like that, which is certainly another way that they can do this. If this is something that you have a student do independently to kind of use as a formative assessment to see where are they at when they're thinking about multiples, that's another thing that you can do because it will show what their thought process is. So for some of them, they're going to start immediately at what are the shared multiples, and they're going to go straight to, okay, let me think through what are the multiples that I know 3 and 5 are going to share, and they're going to fill that out first. And then they're going to start to fill out what are multiples of 3 and what are multiples of 5. For other students, you're going to have them, they're going to fill out their multiples of 3, and they might do just the facts that they know. So rather than skip counting and showing 3, 6, 9, 12, 15's shared, 18, 21, they might just start writing down what they know. So they're going to start with things like 3, and they probably will know their 2's, so they'll know 6. And then the next number that they might know is 15 because 5's. And then 30 is the next common. So typically students know their multiples of 1, 2, 5's, and 10's. And so if you see them do that, then that is an indicator for you. Again, that's how we can potentially use this as a formative assessment of where are they at in that multiplicative reasoning and how are they using that multiplicative reasoning when they are completing this. So again, this is another tool that we can use not only to help students kind of organize their thoughts, but also to see where they are at in that process. And then from a executive functioning standpoint, if you have students who are not thinking through how to do this strategically, who are just kind of writing things down as they pop into their mind, this is an opportunity for you to teach some of that planning piece to them. So helping them think through, okay, what is the most strategic way that we can go about completing this Venn diagram to ensure that we have captured all of the multiples of 3 and all of the multiples of 5. If you have students who are still working on those math facts and you know that the math facts are an area of difficulty for them, then maybe you go ahead and give them these products, and then those students just take the products and are sorting them so that on that particular day, what they're really working on is thinking through what are these multiples rather than thinking through how do I find the multiples. So there are different ways that you can kind of structure these experiences to really tailor and focus to what is the student working on that particular day. All right, so that was an example of a Venn diagram and how we can use that in mathematics instruction. The next one is tables. So tables here, this is kind of a combination of the compare and contrast because in this particular instance, I chose fractions, decimals, and percents because, of course, this is a concept that is critical to not only middle school success, but also high school success for students to understand fractions as numbers and that decimals and percents are, of course, related to fractions and those quantities, and that these things are equivalent. They can be equivalent and interchangeable with one another. So there is this element of compare and contrast when it's presented in this table so that students can see what these values are in their different formats and also discussing them as equivalents. So there is that component. And then, of course, there's also just the component of the hierarchical aspect and what are they being described as in comparison to one another. So we've kind of made a hybrid here of these two different types of graphic organizers. So the definitions themselves, fraction is being defined as an expression in the form of A over B, where A and B are whole numbers. This is a very common definition that is given in textbooks. It is very similar to the definition that is in the Common Core State Standards for Math glossary. This particular definition was taken from the Connected Math Project. So Connected Math Project is a project that is developed here at Michigan State. It's actually done by colleagues in the math ed department, so not colleagues that I collaborate with on a frequent basis, but they have created a glossary with different terms that is where I pulled these definitions from. And so it's just another tool for us as we're thinking about presenting all of these different terms and how they can relate to one another. And one of the great things about Connected Math Project is they really are focused on helping students form connections between the math concepts. And so it's a great resource if you are trying to support students in developing those connections between these mathematical concepts. So the official definition of a fraction is the expression in the form of A over B, where A and B are whole numbers. The relationship then to decimals are we now have a fraction that is written in base 10 numeration. And then the I'm sorry, our pictures are covering my percents, but so I'm not going to be word for word here, but I believe it says something about it is a special fraction that is out of 100, or it is a ratio that is out of 100, because percents, of course, are that fraction that is comparing our quantity out of a possible 100. And then you can see, again, I have used color coding to indicate this is what a fraction might look like. This is what a decimal might look like. And here is what the percents might look like. And then I have real rather strategically chosen some different examples. So we started with 1/1 or 1 whole, and our decimal for that looks like 1.0 or 1 and 0 tenths. And then our percent, of course, is 100%. These things are equivalent. If you wanted to add a fourth column here to the left, you could add a fourth column to the left to indicate to students what these different things are. So it could say term at the top, definition there where the black font is, and then you could put something like equivalent to 1 whole, equivalent to 1/2, and you could write out the word 1 whole, 1/2, 1/4, 8/100ths so that they could see it that way as well. Again, this is balancing your students' needs with what is being presented to them. So the more information that is being presented to them could be helpful, but if you have students who too much information becomes overwhelming or too much to process at one time, then less information that is very strategically chosen to provide those really poignant exemplars is going to be more effective for you. So 1 whole is the first example that we've provided. 1/2, of course, using our benchmark fractions is a really great way to highlight this for students. So we have 1/2 is the same as 5 tenths or 0.5, which is the same as 50%. This is something that students are used to seeing. They have come across this in their everyday lives. 1/4 or 0.25, 25%, and then 8/100ths, which of course looks like 8/100ths written as a decimal, and then 8%. And I chose 8/100ths so that when we're talking about it in decimal format, we can help them draw that connection between, look, when we have 8/100ths written as a fraction, it looks the same as our decimal that we've learned to say as 8/100ths. And because this fraction is already out of 100, we know that this is the same as 8%. The other reason that I chose hundredths instead of tenths is this is a common mistake that students make. It's a common misconception that they have that when they see 8/100ths, we will see students often write this as 0.8 instead. And so helping them really think through, what does it look like in decimal format? What does it mean when we have 8/100ths, and how does that relate to our decimal and percent quantities will help kind of flow that along. Again, thinking instructionally how you might be able to use this. You can present this table to students. You can provide these kind of 4 examples and then have them complete additional examples together in a group, or you can do it as a class together. You can have them provide you with fractions, and then you can talk through, what does the decimal look like? What does the percent look like? You can have them provide you with percents or decimals, and you can talk through together how you would create the fractions and the percents that are equivalent to that quantity when it's presented to you. The other way that I have used this is helping students, sorry, just making sure there wasn't something I needed to address. The other way that I have used this is providing another column to the right where they are finding examples of this in their everyday lives. So helping them think through fractions that they are running across in their lives. So now in our digital age, back when I was a teacher, this was like literally cutting pictures out of magazines. It's funny to think about how far we have come. But now this is taking a picture with their phone when they are driving down the highway and they see a half-mile marker. They can take a picture of it and they can put it in the table to show everybody, here's somewhere that I came across a half. When they are making cookies with their mom and they are using the half measuring cup, they can take a quick picture of it and they can throw it in here to show everybody what that means. Or when they think about a quarter of their football game that they are playing in, they can find a picture of a scoreboard that has a quarter on it and they can throw it in this table, but really using it as another opportunity to help them organize and think through what fractions look like in different settings and what is this real world example of these different things. And also the bonus of the graphic organizer is it's helping them keep it organized, but also extend their knowledge. So the idea is we're taking, if you are familiar with schema logic, right? We're taking our schemas, we know a concept, and then in our mind is making this list of what does this thing mean? What are examples that fall into this different concept? It's filtering out things that don't belong and attaching it to different schemas. And this type of table is helping them create those mental models in their mind. It's providing them a visual example of what could this look like in your mind so that you can keep these things separated and help transition that thing from short-term memory to long-term memory and be able to use it in an accurate way. All right. The last example that I'm going to give before we try some of these on our own is the problem solving process. Now, I will acknowledge that for most of us who have used graphic organizers in teaching before, have probably not used graphic organizers in this way, particularly in math. And that is perfectly fine. Um, I recognize that this one for us cognitively as adults might take more time to really think through and process because it is going to be the most far removed from our prior practices. So, for the problem solving process, this is an example, of course, of our sequenced graphic organizer. You can see here that I have created numbers. We need to go in order 1, 2, 3, 4. This particular attack strategy comes from um, schema-based instruction for problem solving, word problem solving. So I, again, have copied this attack strategy from Project Stair. You can see down there. Project Stair is this amazing project that was created by a collaborative of scholars from across universities. They have made a series of videos to support educators in providing algebraic, um, how do I say this? It's not just algebra instruction, it is like promoting algebraic awareness, understanding, knowledge in our students across mathematics. And so they have different videos on different topics about how you can do this. And one of the kind of I think they have them organized into different modules or different series. One of those series is about schema instruction. And the idea behind schema instruction, without going too far into this, if you have not looked into schema-based instruction or schema broadening instruction, there are several scholars who do this. The Fuchs do this. Jenny Root and her colleagues do a version of this for modified schema-based instruction. Sarah Powell does this. Pirate Math is a fabulous free resource online for grades K through 5 that has different word problem solving activities. But the idea behind schema-based instruction is we teach students the structure of word problems so that, again, they can read the word problem, they can understand mathematically what is happening, and they attach that knowledge onto their own prior knowledge of what that thing is. So, unlike the keyword strategy in math, where we just teach them if you see this word, it means do this operation, it's teaching them when you see this relationship between quantities, what type of problem is this? And there are additive problems and there are multiplicative problem types. And now that I'm thinking about it, I know that I have attended patent conferences on schema instruction from several different scholars. So I know that there are many resources out there for you if you want to learn more about schema instruction. But one of the parts of schema instruction is called an attack strategy. So this is specifically helping our students come up with a plan. What is the plan for this word problem? A plan beyond this is an addition problem I'm going to add, right? We know that for many of our students, they're looking at the word problem, they are maybe reading the words of the word problem. Most of the students that I work with literally just look at the numbers and decide whether they're going to add, subtract, multiply, or divide. They do that with the numbers. I have conducted several interviews with students with autism, and they will straight out tell me they look at the numbers. Based on the numbers, they decide whether they think it is multiplicative or additive just based on the numbers. So if the numbers are like 35 and 5, most of them will say, well, I know that 35 and 5 are multiplicatively related. They don't say multiplicatively, but they'll say like 35 is divisible by 5, so they probably want me to divide. And then they just divide 35 divided by 5, and their answer is 7. So in schema instruction, it is intentionally teaching them to what is your plan? What are you going to do in order to make sense of this problem, come up with a step-by-step idea of what you're going to do, and then arrive at your strategy, or carry through that strategy and then arrive at your answer. The wonderful thing about attack strategies is it provides a structure and it provides a step-by-step checklist without it being too narrow to the specific word problem type, right? When I first started in research, I created a step-by-step heuristic for students to fill out for proportion problems, and it worked beautifully. They filled out that graphic organizer, they crossed out step by step, they solved every proportion problem that I gave to them. But the problem was, as soon as I gave them a different type of word problem, or as soon as I took away that beautiful step-by-step heuristic, they went back to their other way of solving it. And they were not able to solve it because they didn't have the support that I had provided, because I had provided too much support for them. So, an attack strategy like this that is a little broader can help facilitate that bridge between they don't have a plan and don't have a way to come up with a plan. And okay, here's a structure to think through and a way to organize our thoughts and come up with a plan and carry through this plan. And because it is more general, it is more likely to generalize with them to the next problem type, to the next grade, to when we fade supports. And that in that way, this is very effective. So different ways that this can be used. You can present this as a checklist. So again, for my students with autism, they love a checklist. If I give them something like this and I don't put checkboxes on it, they are more often than not going to draw themselves check boxes so that they can check it off. You can laminate something like this and put it on the desk, and the students can go through their own. You can teach them just the mnemonic of UPS check. That is the mnemonic that Sarah Paul and her colleagues use most often now. And so the student, if they are able to remember, understand, plan, solve, check, then that UPS check can become a thing that they go back to and rely on just for themselves. We have seen that for students who learn an attack strategy like this, whether it's UPS check or FOPS or runs or whatever the mnemonic is, we can see them in their work. They'll often write like RUNS at the top to remind themselves of the different steps that they need to take. And then Again, we can be really specific and give them a step by step. What do I need to do? Well, the first thing you need to do is read the problem. Once you have read the problem, then you're going to ask yourself, what am I looking for? So basically, what do I need to know in order to answer this question? And then the last part of understanding is, what do I already know? So not only what do I need to know, but also what information has been given to me so that I can find the answer to that question. Once I have that information, then the next thing I'm going to do is I'm going to record that information that has been given to me, and I'm going to choose whatever my strategy is to come up with a solution. So whether that strategy is, again, if I'm using schema instruction, they're taught to use diagrams and they create a different version of a graphic organizer that is associated with the problem type. But they could also be taught to create an algebraic expression that goes along with the word problem. Whatever their strategy is, they're going to decide what that strategy is in number two, the planning. In number three, they're actually going to then use the plan. They're going to show all of their work so that, again, they can practice that expressive language piece, and they can use that to both justify and to engage potentially in a critiquing situation with their peers. And then last but not least, this is a reminder to label their answer with their unit. So what does that numerical value stand for? What does it mean? And then, of course, one of, if not the most important part of this problem solving process is the check. So checking that their answer is reasonable given the question. So this is coming back to, I'm going to reread the problem and what I was looking for, and then making sure whatever my answer is not only answers that specific question, but also mathematically makes sense. And then they can start to engage in this justification or explanation of what that thing is. And there are graphic organizers out there. I've linked several of them both in the Google document and here in these slides that help with the writing process. I didn't really focus on that today because that's kind of a whole nother beast, if you will, but there are plenty of graphic organizers that can help with the justification or explanation. And Elizabeth Hughes out of Penn State does amazing work on writing in mathematics. So this is kind of the idea behind using this sequenced chart to help students monitor their own problem solving process in math. Just as another example of this, this is work that I did. So this was as I went along, as I mentioned before, I taught students to solve proportion problems, and I used a sequenced graphic organizer that was way too specific. So this was kind of the final version of it that was the most successful for students. And what I ended up doing was putting that sequence within this Frayer model because I found that this helped my students make sure that they were doing something for each one of these steps of the problem solving process. So it was making sure that they were going through and not skipping over things to get to the end. I know we have several students who race through mathematics or they try and do it quickly because in their mind quickly means that they're doing well. And so this was a way that I was kind of forcing my students to slow down and really think through it. Now, what I will say is that for many of my students, after a while, they didn't need to do this anymore. They could fade it. They didn't need both a diagram of the relationship and an equation. They could just write the equation. They no longer needed to think through that visual of I'm comparing paintings to bottles and paintings to bottles, which of course is fine. But we could then use it for when they have to provide that explanation. So when they go to provide the explanation, they went back to filling out this chart so that they could explain to me or show me what this looked like in a visual way that was not just drawing me bottles of paint, but what are those mathematical relationships and how are they related to one another? Again, you can see I drew checkboxes because again, I learned that my students were making themselves checkboxes if I did not make checkboxes. I also started giving students the opportunity to respond in different modes because I was finding that for my students, some of them wanted to tell me while others wanted to write it themselves. And so just providing them with multiple modes of communication so that they could engage in their preferred method for that day for that matter was helpful to them. I was able to learn more about their thinking and get a better sense of where they were when I provided those options. Now, of course, had the luxury of working with them one on one, and many of us do not have that luxury when we are working with students. But it is just another kind of universal design idea of what can we do to support students and make sure that there aren't additional barriers that don't need to be there. All right. So, as I've been talking through graphic organizers, you've probably heard me talk about using them before, during, and after instruction. And so we have used graphic organizers in all of these ways. We can use it to introduce vocabulary terms before we even get started. We can use it during instruction. We can use it as an instructional practice. We can use it after instruction. We can use it when we want to send them home and have them do some kind of homework, but we aren't sure that they are at the stage where they can do this independently. Well, then we can send them home with this graphic organizer to think about and use and draw from as they are solving things on their own so that they have that additional visual support as they are working through it. So again, that's a instructional decision of when are you going to use these things. All right, we have just less than 15 minutes left, and my hope was that we could spend that time creating a Frayer model, kind of practicing. Either you can practice being a student, like how would you do this? Or you can think about how would you lead this as an instructional lesson for students as they are creating this Frayer model with you. So these Frayer models are available both in the slides. So if you already have accessed the slides, then you have the Frayer models. I also uploaded them separately, or they are in the Google Doc, which is available there and as a link in the chat. You can use the Common Core glossary to help you. Don't forget that as you're filling it out, I really want you to practice filling it out in this very different way than I'm sure many of us filled it out before. So the first thing is our term, and all of the Frayer models already have these terms in them. So you'll see a Frayer model for median, you'll see a Frayer model for box plot, and you'll see a Frayer model for congruent. These are just three terms that I have chosen. If there is a different term that maybe you want to practice with, or that maybe you're leading a intervention session later this week and you want to practice using a term, of course, that is perfectly fine. But these are the three that I kind of picked to have us talk through. It's different domains, they're representing different domains of math, but you're going to take the term, then you're going to fill out what are some characteristics and create some visuals of this term. That's the second thing you're going to do. The third thing you're going to do is write down what are some examples of what this thing is. Then you'll do some non-examples. And again, when you're completing non-examples, think of when you're teaching median, right? When we're teaching central tendencies, we're probably also teaching mean and mode. And so when you're providing non-examples, you're probably going to include things like mean and mode because they're being taught at the same time, and you want to explain how median is not that thing. And then you're also going to want to think about what are some common mistakes that you see students making. So I know for me, the most common thing that I see students doing is they don't line up their numbers from least to greatest, right? And so you want to make sure that you are using that space of non-examples to kind of pre-teach or catch them to help them with that aspect. And then last but not least, you're going to go up to definition and you can write either the textbook definition or your own definition of what that thing is. And then you can add your written, you can either do this as a PDF, you can um, animate it in that way, you can type it out, however you kind of want to do it. You can recreate it in the Google Doc if you want to create another slide and do it in there. But the hope is that as we're creating it, we can kind of see from each other how each of us are defining and characterizing these terms in similar but slightly different ways, if that makes sense. And then we'll just do this for a few minutes and then we'll come back for questions. So, um, can everyone access the Google Doc or the slides to start thinking about what this might look like? Okay, awesome. I'm seeing some head nods. So let's just take a few minutes, start filling this out. You're not going to get a full Freire model completed, and that's perfectly fine. Just start making yourself do this and feel what it feels like. All right, just take a couple more seconds here. Okay, I'm going to move on so that I have enough time for questions. The goal of this exercise was really to provide you with an opportunity to feel what it feels like to think about terms and explain terms in this way, and the kind of cognitive process of taking that information and writing it down, putting it in these different categories. I will upload to the Google Drive later today and into the patent portal. I will upload some examples from a student perspective of what these things look like since we didn't have time to talk through them together. Okay, but for now, first I will say there are additional resources in that Google Drive. There are several articles that I mentioned today and did not. There are templates for you to use. There are other additional links for your perusal at some point. But if you have questions or comments at this point, I would be happy to take those now as well.